In the last video, we used our factory pattern to implement power-ups in our Brickout game. In this video, we're going to cover a feature of Pygame that we haven't talked about yet, masks. We'll see how to use masks to improve gameplay and implement some cool drawing effects. Let's get started. First, I've moved the droppable and power-up classes to their own script because our program is getting long. I simply import the classes I need from that script at the top of the main game script. So if you're grabbing this code from my GitHub repo, make sure you get both powerups.py and brickout90.py. Let's talk about masks. Pygame has a mask module with a couple of methods for creating a mask and the mask class. There's actually some mask code already in this program. I used a mask to give our paint droppable objects a random color, but I didn't go into depth on how it worked. Let's do that now. In the paint droppable init method, I create a mask from the paint drop image and then use that mask to color the image. Let's break this down step by step because it's a good introduction to what masks are and how they're useful. First, I have the line of code self.mask equals pygame.mask.fromSurface image. FromSurface is one of the mask module methods that will create a mask object. FromSurface creates a mask from a surface. And what is a mask? It's a grid of ones and zeros that's the same size and dimensions as the surface it was created from. The mask object has a 1 anywhere the surface has a non-transparent pixel, and a 0 anywhere the surface has a transparent pixel. So with the paint drop itself is made up of visible or non-transparent pixels. Those are all ones in the mask. But all around the paint drop are transparent pixels, pixels with an alpha value of 0. Those are all zeros in the mask. Remember, every surface is a rectangle, so to get it to look like it's a paint drop shape, we make all of the pixels around the paint drop transparent, or we give them an alpha value of 0. We could also use a color key, as we do with the ball, and if a surface has a color key set, then that is used to determine which pixels are transparent, and therefore will be zeros in the mask. Back to the init method, we then iterate over all of the pixels in the mask, one at a time, and if the mask pixel is a 1, we color the corresponding pixel in the paint drop with our random color. If it's a 0, we don't. We use the mask method getAt and pass in an xy tuple to get the pixel at xy in the mask. And we use the surface method setAt and pass in the xy tuple and the color to set the color of the pixel in the surface. Both masks and surfaces have getAt and setAt methods. With a mask, getAt and setAt are working with only 1 and 0 values, and with a surface, getAt and setAt are working with a color tuple. We'll see a less labor-intensive way to create a colored surface from a mask later in this video, but I wanted to show you getAt and setAt because those are very useful methods. Let's take a look at the other method that creates a mask, FromThreshold. You might notice that my paint drop isn't solid blue. It has some reflection in it that's white. When I create the mask, because those white pixels aren't transparent, they are all ones, and they get filled with the color, so I lose the reflection in the paint drop. Suppose we use FromThreshold to create the mask. Let's look at the parameters. It takes a surface to create the mask from, a color, an optional threshold, an optional second surface, and optional palette colors. This can work two different ways, either with the color parameter, where it makes a mask from the first surface for all pixels within a threshold of that color, or with the second surface. In that case, it makes a mask for all pixels on the first surface whose color values are within a threshold of the corresponding pixels on the second surface. We're going to use the first method. This will set mask bits if the first surface has a bit within the threshold of the color. Best practice is to sample the color from the surface itself and not to hardcode that color in, just in case the image is altered in graphics software or somewhere in the program. Of course, what pixel do we choose? I'm going to get the center pixel. That should work for both of my paint droppables, the paint drop and the gummy bear. So for every pixel within the image that is within the threshold for each color channel of the center pixel, we'll add it to the mask. For my paint drop, the center pixel is blue. I want all the blue pixels to be in the mask, but none of the white pixels that make up the reflection. So it looks like there's a reflection no matter what color the paint drop. So I'll write image color equals self.image.getAt self.rect.width divided by 2, self.rect.height divided by 2. And then self.mask equals pygame.mask.fromThreshold, image, image color, threshold equals 10, 10, 10, 255. Let's talk about that threshold. It is a tuple of red threshold, green threshold, blue threshold, alpha threshold. The default threshold is 0, 0, 0, 255, so technically that would be an exact color match regardless of alpha. In practice, I've found that a threshold of a few pixels, in my code 10, produces more reliable results, so that's what I'll use here. And when I run this, with the mask made within 10 of the blue threshold, I get different color paint drops with the white reflection. At the end of the video, we'll look at another cool drawing effect we can do with masks. But first, let's see how to use masks for collision detection. Let's go back to the documentation for pygame.Sprite.Group collide and talk about the last parameter to the function, collided. It has a default of none, and we've never passed in an argument for that parameter. What is collided? The collided parameter is a function that will take two sprites as parameters and return a Boolean, true if they're colliding and false otherwise. So if we pass the name of a function here, that function will be used to determine if there's a collision. The default method of determining if there's a collision is to use the sprite's rectangles. This is fine for rectangle-shaped sprites. For non-rectangle-shaped sprites, it's better to use the sprite's masks to determine a collision. If we have unusually shaped sprites, their bounding rectangles might intersect without any visible part of the sprites intersecting. If the game responds as if the sprites collided, even though there was no visible touching, that feels unnatural to the player. Now, there's actually very little we have to do if we want to use masks for collision detection. Let's modify our game to use masks for all collisions. For each of our calls to group collide, we're going to add an argument for collided. Luckily, we don't have to write the collided function ourselves. There's already a function in Pygame that checks for mask collisions, called collideMask. So we'll just pass that in as the last argument to each call to group collide, pygame.Sprite.collideMask. That's step 1. Step 2 is for efficiency. Sprites have a mask field, but if we don't set it, then the collideMask function will create a mask for each sprite each time it's called. You might have noticed in my paint droppable init method, I stored the mask in self.mask. That's the name of the mask field for sprites. If we give that a value, collideMask will use it. So we should create a mask from the image for each sprite for each time the image changes. Right now, we're not changing images very often, but for example, when the paddle enlarges and shrinks from a power-up, I'll need to make sure I'm changing not only the image field, but also the mask field, or we'll get some crazy bugs. I'm therefore going to comb through my code and put self.mask equals pygame.mask.fromSurface self.image in each init method after setting the image, but I'll also look for any places that the image changes and recreate the mask there too. I'm only going to do that for sprites that take part in collisions. I don't need to do it for the scoreboard or for power-up. When I run the game, you're probably not going to see a big difference in the collisions. Maybe there is some improvement when the edge of the ball collides with the edge of the paddle. But it's going to be very important with larger sprites that are oddly shaped and that can move freely around the screen. You don't want your player character to lose health in a top-down or side-scroller because they collided with a monster's rectangle but not the visible pixels of the monster itself. So remember, 2 steps to using masks for collisions: setting the mask field in your sprite in init and anytime the image changes, and passing collideMask as the collided argument to a collision method. I promised a fun effect with masks, and if you're interested, I have a video showing 5 fun things you can do with masks in Pygame, which I'll link here. We're going to do something different here. I'm going to run this and show you the effect first. Notice when a paint droppable hits the paddle, instead of completely coloring the paddle, it makes a splatter on the paddle, exactly where it hit the paddle, in the color of the paint drop. In the PowerUp Factory's getPowerUp method, I've added some parameters. First, the droppable. That's so the PowerUp can get any information from the droppable that it might need, such as the color of the paint drop. And second, I've added a coordinate, caught X and caught Y. That's the exact spot on the paddle where the PowerUp hit. I've also changed the Effects Manager and Paddle Artist classes a little bit so that the Paddle Artist registers the color and location of the color with the Effects Manager when it's created, and it doesn't ever remove it, although it could. I thought we'd just let the splatters build up. The most interesting code is in the game. First, when we handle a collision between the paddle and a droppable. How do we get the collision point? We can use the overlap method of a mask to get the point where the masks overlap. I want to know that point in the paddle's coordinate system, so I am sending the overlap message to the paddle's mask. For arguments, I pass in the droppable's mask. I also have to pass in an offset, the coordinates of the droppable in the paddle's coordinate system. Masks are like surfaces. Their top left coordinate is 0, 0. If I want to know where the droppable is in the paddle's coordinate system, I'll have to calculate the offset between their corresponding rectangles in the game's coordinate system. I do that by subtracting the paddle rects x and y from the droppable rects x and y. This gives me the location of the paint splatter on the paddle. Let's look at how we draw that on the paddle, which also uses masks. I've added the colors to the paddle as a dictionary, where the color is the key and the location on the paddle is the value. And the paddle obtains those from the Effect Manager in Update. I've also created an image of a splat. I load that in init and get its mask. That's a field of the paddle. When the paddle draws itself, it draws its rectangle and fills it with blue, and then iterates through its splat dictionary. For each color in the splat dictionary, it creates a surface from the splat mask using the mask to surface method. That will create a surface with colored bits where the set bits in the mask are. There are two optional arguments to the mask's toSurface method, setColor and unsetColor. I pass in the splat color for setColor. All of the set bits in the mask will be colored that color. And I pass in a fully transparent color for the unset color, so that will allow our splats to layer over each other. This is a great method for getting a color surface from a mask if you need the surface to be only one color. And the effect is really fun. The paint splatters layer on the paddle as we catch them. So there you have it, the Pygame mask module and mask class, with several different examples of how to use the mask class in your program for drawing and collision detection. For homework, you might consider one of the effects I go over in the 5 Cool Things video, such as adding a glow or a shadow to the ball, bricks, or paddle. I'd change the background color if you're going to add a shadow. You could also try adding a crack to a brick where the ball hits it, rather than making the brick disappear. If you get stuck or want to share your successes, drop a comment below. And as always, have fun and keep coding.